You know how to let me chat, all right? I see. Okay, we have other ideas of particular subsets, okay? And so, as was the intriguing thing for the Pakistani friend, we have again that we have an idea which is interesting in sets. Let's see what it can be, how it can be translated into edges and conversely. And so we had this idea of covering. Why not edge covering? Can we have a notion of edge covering? Of course. And it is like this. It's a subset of the set of edges such that each vertex of G is an end of some edge in L. Okay? At least one edge in L. Okay. And there are already differences. While you always have a covering, not always can you have an edge covering. When it's not possible, if you have isolated vertices, meaning with degree 0. A vertex by itself is a normal possible vertex, but of course you don't have an edge covering if you have an isolated vertex, okay? While you always have coverings. And, okay. You denote the, we already had matchings, okay? And so you can see this thing. Matchings, like the translation in terms of edges of independent sets, or conversely, if you want. And now we invent edge coverings as a translation in terms of edges of coverings, all right? And so it's quite natural, even if you see already some big differences, one always exists, this one not always, we can think, well, what about a relation like the one we have just seen, alpha plus beta equals ni? Is there some relation like this? And so we call alpha prime of G the number of edges in a maximum matching, okay? And beta prime the number of edges in a minimum edge covering, all right? And what happens with something which is much more complicated to show, that alpha prime plus beta prime equals ni again. And that's very surprising because the theory is quite different, okay? And so here we have this alpha prime plus beta prime equals again ni, okay? Oh, by the way, here we see an independent set. Again, we see even if the book talks not so much about maximal and the difference with maximum. Here we have an independent set, and it is maximal, even if it is of just one vertex. Why? Just add any vertex to this set, to this black set, and you will not have anymore an independent set. Okay, why? Because this vertex is adjacent to all others, so you cannot add an edge vertex to this independent set. So it is maximal, even if it's not maximum. This is a maximum, and of course also maximal one, meaning that with these two, you get an independent set, and however you add a vertex, you get something which is no more independent. Okay? All right. And then a nice thing is that you have also, even if the theories are actually different, you have a similar relation to the one we saw before between coverings and matchings. And now we have a similar thing between edge coverings and independent sets. meaning what? What we have there, that in a bipartite graph with at least 1 as a small delta, the number of vertices in a minimum independent set is equal to the number of edges in a minimum edge covering. Okay? I don't know how to write it. Anyway, maximum independent equal. Anyway. Okay, and also okay. No, all right. That's all what we have here. Okay, so you see among all these that we have a set of relations, and all the times we have conditions of maximality and minimality which are interfering with each other. Now we go to Ramsey's theorem. And Ramsey's theorem is something which, in my opinion, should be rather amazing, even for you who are not particularly interested in this sort of things. And first, something about that guy. Frank Ramsey was an enfant prodige, a genius boy, okay? And he was, above all, I think he was a philosopher, and he interacted with Ludwig Wittgenstein. And in particular, before he interacted with Wittgenstein, his professor gave him the book of Wittgenstein in German, and Ramsey, an Englishman, did not know German, and so the professor said, well, learn German and read this. And it seems that in less than 1 week, Ramsey learned German and was able to translate and make the official translation of the treatise of Wittgenstein. So not a pink Roman or something like that, but a very deep and difficult text. Okay, and so just for saying something, and he was active in philosophy, active in economics, and active in mathematics, and he died at 26. So all he did was, before 26, and for a very stupid operation with septicemia, so he got infected during the operation, and he died for that, and it's extremely strange. Okay, it's the period is the 30s of the last century, so it's strange that they had such problems. And he was not a poor person, okay? And so it's strange that he did not get cured in a correct way. And so he died at 26. But he was able in between to do something like this. Now, please, even terrible ladies should pay a little bit of attention, because I think this is a real peer of mathematics, okay? And so, for all the rest, you can continue. I'm pretty sure that you have quite interesting things to talk. But please, just for Ramsey's theorem. The idea of Ramsey's theorem is this. On one side, you have independent sets. Sets of vertices, no two of them are, which are adjacent, okay? No edge between them in the given graph. On the other side, you have what is called a clique. A clique is a subgraph which is complete. So it's exactly the opposite, meaning vertices which are all joined, all adjacent one to the other in the graph, okay? So they are the two extremes that you may have as subsets of the vertices of a graph, okay? And what happens if you, what do you think that you will have with high probability if you have few edges? You have you have 100 vertices. Will it be more probable to have independent sets or cliques if you have a few edges? Independent sets. And if you have quite a lot, cliques. And you might think one could do some good probability theorem about that. Okay. Oh, there is also a whole part of graph theory which is probabilistic graph theory, but it's not this one, because this is not probabilistic. The Ramsey's theorem says, okay, give me two positive numbers, okay, k and l, and there exists a number called the Ramsey number of k and l, such that every possible graph with at least that number of vertices either has an independent set of okay, well, what is the one on one side? Either a clique of k vertices or an independent set of l vertices, okay? Either a clique of the first or an independent set of the second number of vertices. This is not probabilistic. That means take there is a small table. The actual table for now is not much bigger than that. So let's take this. No, a nicer one. 9. I don't know. This one. No, this is nicer. 4 and 3 and 4. Okay. If you draw any possible graph with 9 vertices, then either it has a clique of 3 or it has an independent set of 4. Don't you think it is rather striking as a theorem? It just says give me the number of vertices and draw the graph as you want. And it's not a matter of probability. It's totally certain that either you have one or you have the other. Of course, what's the trick? The trick is that one is the opposite of the other, if you want. Okay? But the interesting thing is also that this table is of 1977. The table of now is not much bigger than that, in the sense that they have discovered other Ramsey numbers, but for many you just have intervals. You know that the correct Ramsey number is in that interval, but the numbers already completely known are maybe surely not twice that table there. Okay, but let's see how we can face that. I will not give you the proof, unfortunately. I was tempted to give you the proof. It's very nice, but let's see the starting of it. Okay, let's see, for instance, that R1L is 1, that RK1 is 1. What's R1L? It means the Ramsey number for one clique of 1 or independent set of L vertices. Now, it is 1. Why and what does that mean? It means if you take any graph with exactly 1 vertex, okay, either you have a clique of 1 or you have an independent set of L. But what is a clique of 1? A clique, I recall, is a subset which induces a complete subgraph. So a complete graph of one vertex, how is it?
This K1 is a complete graph. It has one vertex and no edges.
One vertex and no edges. And so, of course, if you take just one vertex, it's completely true, and you don't have the L independent sets. You just have a clique of one, necessarily, if you have a vertex, just one vertex, okay? On the other hand, if you have a RK1, why is it 1? So, either a clique of K vertices or an independent set of 1. Yes, but an independent set of 1 is just one vertex, and so if you have if you have a graph with at least one vertex, of course it has at least one independent set of 1. Okay, the vertex itself. And whatever you take the graph, you pick up just one vertex, you can consider it a clique of 1 or an independent set of 1. No problem. But this is maybe looks very trivial, but it is necessary for what follows. Let's see what happens with 2. Now, R2L equals L, RK2 equals K. Let's see why. R2L equals L. It means if you take any graph with at least L vertices, either it contains a clique of 2 vertices, or it contains an independent set of L. Why is it so? Let's see, when you have mysteries in front of you, always go to the definition. And so, an independent set of L, what would be? If it is a graph with L vertices, let's put numbers. R210, okay? R210. And so they say R210 equals 10. So if I have a graph with 10 vertices, can it have an independent set of 10 vertices? Yes or no? And if yes, what would be the particular condition for it being so?
No edges.
No edges. Okay, but that's possible. I have 10 vertices and no edges. Isn't that an independent set? Sure it is. No, it has one edge. But then one edge, what is it? How can you consider it? Consider the 2 vertices of that edge. 2 vertices, one edge in between. Isn't this a complete graph with K2, the complete graph with 2 vertices? And so, you have an edge, at least, then you have a clique of 2. You don't have edges, then the whole graph the whole vertex set is an independent set. Okay? On the other side, RK.
What's the difference in the complete graph and the regular graph?
Regular graph is not necessarily complete, but the complete graph is necessarily regular, meaning a regular graph of some degree means at each vertex you have the same number, the same degree k. Okay, and so if you have the complete graph with 7 vertices, all of them have degree 6, and so surely K7 is a 6 regular graph. Okay, but you might have 7 vertices and irregular or degree 2, a big cycle of 7. Okay. Regular or degree 2. Each vertex has degree 2. Just join them in a big cycle and that's all. Okay, just for saying the possibility. Okay, but let's come back to here. RK2 equals K. Why? So it says R2 10 equals 10. If I take a graph with 10 vertices, either it contains a clique of 10 or it contains an independent set of 2. Is that true? And if it is, what are the situations? Graph of 10 vertices. Can it contain a clique of 10 vertices? Yes, but only if don't suffer, think. 10 vertices, okay? Any graph with 10 vertices, this is what they are claiming. Either it contains a clique of 10 or it contains an independent set of 2. Okay, what is an independent? Let's start from this. What is an independent set of 2? What is an independent set? But please mind, I've already said today many times what an independent set is. Okay? It is a set of vertices of this graph such that in any way you take two vertices of this set, they are not joined by an edge. Okay, so if I say an independent set of two vertices, what does that mean? Two vertices without any edge. Is it possible that you have in a graph with 10 vertices, two vertices which are not joined by an edge? Is that possible or not? Is it always so or always? If it's not complete, if it's not complete, it means what does it mean that it's not complete? That at least one pair is not connected by an edge. Take that pair. It is an independent set of two. She seems not to follow, but she does, you know, even while she's talking with a friend. Okay. And the other possibility when you do not have this one thing is what? That it is a complete graph. Then if it is a complete graph, it means that itself it is a clique 10 by itself. So it is complete, it is a clique. It is not complete, there is at least one pair which is not non-adjacent vertices, and that is what we are looking for. Okay? Good.
What is the definition of clique?
Clique is a subset, clique in a given graph G is a certain subset S, say, of vertices of the graph, such that the induced subgraph, meaning take those vertices and all edges connecting these vertices,
Complete subgraph.
is a complete subgraph. Okay? And so, a complete subgraph, a clique of 2 means just an edge, as the lady was saying before. Just an edge, a link, precisely, is a clique of 2. A vertex by itself is a clique of 1, and so on, okay? But now, the interesting thing is this theorem, which says, for any two integers, k greater than or equal to 2 and l greater than or equal to 2, you have such a number, rkl, which is less than or equal to rkl minus 1 plus rk minus 1 l. Okay? And so, for instance, this can be seen as a recursive thing. Why? Because you can start, for instance, with L equal to 3, and you can use what you have here, going to RK2 for this, and K equal to 3, and you can go down here with that, okay? And so out of this and this, you can get these two numbers. And so there exists this number, which is under these two, the sum of these two. And so, drawing from below, since at the beginning we can see, as we had just done, we can see what these numbers are, due to this theorem, we can say that these numbers exist, and we know where they are, okay? They are below a certain number, which we already know, if we know the previous ones, all right? So, what can you get generally? You can get upper bounds out of this. But this means that these numbers exist because you have upper bounds, okay? Not only, but then you have really an artistic side of this research, which is, okay, find lower bounds. How can you find lower bounds for Ramsey numbers? It can be done with what are called Ramsey graphs, meaning graphs for which you don't have that particular possibility. Okay, let's see. For instance, well, what about this? Here, what can we find of big enough? Can we find, can we find an independent set of 3? No. Can we find a clique of 3? No, a clique of 3 is very simple, it's a triangle. Okay? So, this shows you that Ramsey number R of 3 is surely greater than 5. Okay? What is Ramsey number 3 of 3? Is that number such that any graph with at least that number of vertices either has a clique of 3 or has an independent set of 3. Now I have one which has neither a clique of 3 nor an independent set of 3, and so necessarily that number, which we know existing by the inequality of before or previously seen, then it has to be greater than 5, okay? And this gives you the first number out of it's before, sorry. It tells you that it's at least 6, but out of oh, okay. Let's go on. We have here other Ramsey graph. This one is not a vertex, okay? And so this is a graph with 8 vertices, and here this is a 3-4 Ramsey graph, meaning that here you don't have a clique of 3 and you don't have an independent set of 4, okay? So by just giving examples, you can say this is not respecting neither conditions which we would like for 3 and 4. And so, since that is 8, we know that R34 is at least 9. And also with this one, which is a 3-5 Ramsey graph, and this one, which is a 4-4 Ramsey graph, we know these inequalities. But then, what can we say? R33 is less than or equal to R32 plus R23, correct? And that is the inequality we saw before. But that we know that it is 6, and so since we had this by the example, by that particular example, and that by the inequality, then we know exactly that Ramsey number of C3 is exactly 6. Okay? And so on and so forth. Actually, there are some tricks due to the fact that the inequality has also a particularity. The inequality is not just this inequality, but if you have RKL-1 and RK-1L, which are both even, then the inequality is strict. Okay? It's all in the same proof. And then out of this and out of the examples that you have seen, you can get the Ramsey numbers that are shown here. Okay? All right. That's all that I wanted to tell you about this. Okay? I don't think that we have more in this chapter. Yeah? And, okay. Next, no applications here. Next, I want to go and solve some of the problems I left from the previous class, and maybe start at the initial definitions of the important chapter, vertex colonies. Okay? 15 minutes break. At 10 past 5, I start actually.